Hello everyone. Today's video shall remain untitled for now. You'll find out in due course what is the title of today's video as well as what is the point of today's video. Obviously this is a Math Olympiad channel. We are going to look at some Olympiad problems. And I think you are going to find out by the end of this video what is the point of this. But minimally, we'll look at some interesting questions. So without further ado, let's look at our first problem. Our first problem is taken from the SMO Junior 2020. If m greater than n are positive integers satisfying m squared minus n squared squared equals to 1 plus 80n, what is the smallest possible value of mn? I'll pause for a moment to let you think, and feel free to pause the video if you want to try it on your own. So, when I look at this question, as an SMO Junior problem, I kind of look at m squared minus n squared and I feel like doing a difference of squares. We talked about this not too long ago, but it doesn't really do much here. And then maybe we would consider also to move the 1 over and do that with a difference of squares. Unfortunately, that does not really do much either. And so this is rather peculiar. If we try to expand it, it's not very good either. And so this is the point where we are getting a little bit concerned. Why am I not making any progress? Why is it that all the most obvious things that I may consider does not seem to work? Now, in order to solve this question, what we need to do is to just think about Diophantine equations more broadly. We need to think about Diophantine equations more broadly as being equations that usually have some interesting property or are impossibly hard to do. For it to be an SMO question, there must be something interesting. And the interesting things usually, if you can't factorize meaningfully, either have to do with some sort of modular arithmetic condition or have to do with some sort of bounding argument. I'm thinking that modular arithmetic might not be such a great thing here because for modular arithmetic, we usually use it to rule out solutions, but it doesn't help me to find the smallest possible value. So I'm going to try to bound this, and my bounding argument is going to start from the fact that m squared minus n squared is still pretty big to be then squared. Now you might say that, well, I mean, why does m squared minus n squared have to be big? And my answer is that I'm not really saying it is big. I'm just saying it's big compared to the right hand side 1 plus 80n. The loosest bound is that, and the best bound at the same time, but the simplest, loosest, and the best bound is that n plus 1 squared minus n squared is the smallest possible value of m squared minus n squared. And so, which means that the left hand side is greater than or equals to 2n plus 1 squared, which means that somehow 2n plus 1 squared is less than or equal to 1 plus 80n. That is quite tiny, to be honest. It gives me, however, a simple quadratic inequality. Cancel off, move it over, and that I can factorize. So n goes from 0 to 19 is going to be the range of values that I need to try. Now incidentally, if n goes from 0 to 19, then of course the smallest possible value is not necessarily 19. I still need to test out the rest of the values, but this already restricts it a lot, because if this is going to be 1 plus 80n, where n goes from 0 to 19, it's going to be at most 1521, which is a square, which is 2n plus 1 squared. When n is 19, it is 39 squared. But I want the smallest, so I need to just check, could there be any others in this range? Now to check that, the last digit of this has to be 1. Now, the last digit of this has to be 1, so the possible squares up to 1521 I just check them. Now 31 squared equals to 961 is interesting, because this provisionally could give me n equals to 12 if it were possible to make m squared minus 12 squared equals to 31. Nah, that doesn't work. You can just get, this is 175, that doesn't work. So it turns out that what we guessed at the start, which is that only n equals to 19 and then m equals to 20 works. So smallest possible value is 380. That's pretty hard for a junior round 1 question, wouldn't you think? If this is concerning you a bit, fair enough. Because it turns out that this was actually a senior round 2 question from the year 2004. With the number changed a little, the variable names changed a little, but substantively, I'm sure you can see it's the same question. Now there are a couple of things you could make of this, right? The first conclusion you could say is that, oh, so does that mean that the SMO was so much easier last time than now? Well, there is some merit to the fact that generally over time, the SMO and most Olympiads do get, in a sense, more challenging. But there's also something to be said for the fact that every paper has difficult questions and easy questions, and also that what feels easy or difficult is very much something that is a byproduct of the time in which the question is being set. So something like this would have been a lot more difficult perhaps in 2004 than it would be right now. Now I would say a bit more about this, but hold that thought as we now look at a more recent senior round 2 question. This is from 2017. It's a functional equation where we are asked to find all functions such that f of k plus 1 is greater than f of k for all k greater than or equals to 1. Your function is from positive integers to positive integers, which means that technically speaking, this statement here just tells you a list of inequalities. And so on. So this is the whole set of information which you have available to you at this particular moment. I'm sure you would find it obvious that fx equals to x works. But what is a little bit more tricky is to figure out if there's anything else, right? This sort of functional equations, there's always some chance of an exotic solution working. The previous video we alluded to the pointwise track, right? Maybe it is fx equals to x most of the time, but somewhere it's not, right? How do we know that? So it is potentially a risk. I cannot assume that. Now, I've also alluded to a question, argument of this sort in a previous video where we talked about our without loss of generality assumptions. One of the things we highlighted was that when you have got the set of positive integers, it behaves differently from the set of integers. Because any set of positive integers must always have a minimum. Now I'm looking at this here, and my idea is that in the set of things in the range, there must be a minimum. Let's call it f of a. Now everything here is in the range. So is everything here, right? Everything in here is f of something. So the range contains all of these. Now that means that f of 2, f of 3, f of 4, f of 5, and so on, these are not the minimum. And if these are not the minimum, well, what is the minimum? Surely it must be f of 1. Now, it must be the minimum because the rest of them are not the minimum. In fact, everything else in the set is bigger than something else. So where's the smallest guy? The smallest guy must be f of 1. And in fact, all of these are just all bigger than it. Now, at this point in time, we don't yet know what f of 1 is. I think it is f of 1 equals to 1. But I'm not sure. What I do know though is that everything else in the list here is not 1. Right? So I don't know whether f1 is 1. I know that all of these are at least 2. Now what that implies is that each of these here is all going to be at least 2 now. And so that means that f of 3 is bigger than f of something more than 2. F of 4 is bigger than f of something more than or equals to 2, and so on. That would now imply that if I look at the set f of 2, f of 3, and so on, this has a minimum that must be f of 2. Because once again, everything else is bigger than something else in this set. So f of 2 is going to be the minimum of these. which means that now you've got f of 1 is less than or, well, strictly less than f of 2, which is strictly less than all the other stuff. And I think you can see where this is going, right? We are able to induct and show that this is strictly increasing. This is strictly increasing, which means that specifically, f is an increasing function. And when f is an increasing function, what that implies is that f of k plus 1 is greater than f of k. You can strip off one layer of f from the outside. Larger inputs give larger outputs. And therefore f of k is less than k plus 1 for all k. And it turns out that it really was f of k is k. Collectively, this and this, not too hard to tell, you just get f of 1 is 1, f of 2 is 2, and so on. Whoops, forgot to write down what the function is. You can see that this is conceptually quite mind-bending, right? And once again, I have not written out a very full solution. If you wrote it in full, it would easily take one page. Some of you are going to say, oh, this is actually really hard. Like, this is senior round 2. I'm in a lot of trouble. This is really, really hard. Well, it is true that the senior round 2 is really hard. It is also true that this question actually was the last question of the IMO from, well, quite a long time ago, admittedly, but it is actually the last question of the IMO 1977. Not only is it the last question, but the IMO question was actually kind enough to tell you straight away that Fn equals to n, so that you don't have to even speculate whether that is the only solution. Okay, let me make clear that the IMO in the 1970s and 80s is in a way easier than now. At the same time, that is heavily influenced by the fact that questions in the IMO from the 1970s and 1980s show up in things like the SMO Senior, right? So obviously, by the fact that they show up, you have learned these ideas, and so you look back and they don't look very hard anymore. Would you have done it if you knew that this was a IMO Q6? I cannot say for, and I am sure that most of you cannot say that you can confidently solve every IMO Q6. What I can confidently say is that if you were to go into, let's say, the math department of any reputed university, there are only a handful of professors who would say that they're confident of being able to solve an IMO Q6 within 3 hours. That could be in Singapore, that could be in the US, that could be in the UK. Obviously, when I say confidence, there's different degrees of confidence. But would you have even tried the question if I introduced it to you as an IMO Q6, or if your teacher introduced it to you as an IMO Q6? Perhaps not. See where this is going? Now, this is another IMO question that is pretty famous. It's pretty famous because it has been solved in a bunch of different ways. The methods include substituting, like A equals x over y, B equals to y over z, C equals to z over x. This is method number 1. After you do that, then things will turn out to be not too bad. You can use AMGM or you can go ahead. Another method that is also known is that you can do this by using Cauchy-Schwarz in the form of T2's lemma. There are other methods, but this is not the main point of this video. It is not a video where we're going to keep on solving IMO questions. Otherwise, the runtime of this video will be much longer than what you're seeing right now. This is an IMO question. It appeared years later as our SMO Open Round 1 problem. I took this SMO Open in 2014. When I saw this, I was very conflicted. I'd seen the IMO problem. I was very conflicted because on one hand, I felt that what on earth are they thinking, putting an IMO question in the SMO Open Round 1? It's way too hard to solve properly. Then I felt a bit happy. I'm like, oh, but I do know how to solve it, right? So then I actually have an advantage over everyone else who has not seen it before, because no one can possibly solve an IMO question during the duration of the SMO Open Round 1 with 24 other questions. Then I thought a bit more and I said, you know what, this is just very sad, because among other things, the equality case is just 1, 1, 1, right? You just get the answer. It's 3/2 times 2014 because they have scaled it up. And this is pretty sad. But what I felt sorry for is if anyone actually tried to solve this in the SMO Open properly. Because if you try to solve this in the SMO Open properly, without having seen it before, there is very, very, very scant chance you're going to solve an IMO question in 5 minutes. We can have a debate another day, or you can write in and complain to the Singapore Math Society another day about why are they putting IMO questions into the SMO Open, or you can just guess that it is all one. You're seeing the problem here, right? So again, if let's say that you saw this as an SMO Open problem and you can't solve it, you might be thinking, why is this Open Round 1 question so hard? And then after that, you realize it's an IMO question. Now, let's look at one final example. This is from Singapore's IMO team training materials. So it was used as a practice problem back in 2003. The questions here is asking you to find the smallest positive integer n such that among any n irrational numbers, there exist 3 numbers such that the sum of any 2 of them is still an irrational number. Take a while to process this, if you will. Pause the video if you want to think about it. Now this says any n irrational numbers, there must exist 3 of them such that the sum of any 2 of them is still an irrational number. So from an experimentation perspective, I would try to make a lot of pairs of them that are not irrational numbers in order to so-called rule out values of n. For example, n equals to 3 fails because I could just have my numbers be pi, 1 minus pi, and let's say square root 2. Now obviously these 3 numbers, the sum of these 2 would be rational. Now if I use n equals to 4, then I could have just done the same construction, except that now I have 1 minus pi root 2, 1 minus root 2. And by pigeonhole, if I pick 2 of them, so I pick 3 of them, two of them was be in the same group, sum to 1. So n equals to 4 doesn't work. Now for n equals to 5, that's where things get interesting. Now, I kind of want to make it fail, not by creating a new irrational number. If let's say I created a new irrational number e. Actually, this is a bad idea. It's currently an open question whether pi plus e is an irrational number or rational. So let's not use e. Let's use square root 3, right, as what I don't want to do. If let's say that I did this, no good, because the sum, if I took this tree, the sum of any two of them is irrational. Now, if let's say that I were to try to be smart, say, okay, I don't want it to be that way, I'm going to do 2 minus pi. So that now if you pick pi, and you pick 2 minus pi from here, then you see, two of them are going to sum to rational. Well, I could technically have avoided it by picking these. Now what happens is that as we're doing this, at some point, some graph theory idea is going to pop into your head. You're like, oh, okay, so actually I can connect those which have a rational sum. And what I would like is to find 3 of them which has no edge. Now I'm going to want to know whether for n equals to 5, it is possible. So I'm going to erase off these pi's and root 2's for now, and I'm going to kind of do it as a graph. Now, if you do it as a graph, the idea is that I want to ask, is it guaranteed we can find an empty triangle? And of course, I want to connect those with a rational sum. What I saw just now is that whenever I tried to set up, let's say pi, 1 minus pi, and 2 minus pi, 1 minus pi and 2 minus pi do not add up to a rational number. My question is whether it is possible to actually make further progress. So what I'm going to do is that I'm going to develop some lemmas. The first lemma I'm going to say is based on what I've noticed, which is that there is no triangle. What does a triangle mean? A triangle means that A plus B, A plus C, and B plus C are rational. You see what goes wrong here? Essentially, that means that their sum, which is 2 times of everything, is rational, which means that A plus B plus C is rational, and you subtract off, it means A, B, and C themselves are rational, which is a contradiction. So therefore, there are no triangles. Okay, so at this point, I'm looking at it and saying, okay, there's no triangles. What does it mean for my chances of getting an empty triangle with no edges? Well, the first case is that there is a vertex of degree 4. Now this is for n equals to 5. If I have a vertex of degree 4, because there are no triangles, this is empty, this is empty, this is empty. I found an empty triangle already. In fact, I don't need degree 4. I've got degree 3. If any vertex has degree greater than or equals to 3, there is an empty triangle. Now remember, I'm trying to avoid empty triangles. Now let's say that I have, on the contrary, I have got a vertex which is not connected to most things. So it's not connected to 3 things. So not connected to 3 things means degree is at most 1. So if any of them has degree at most 1, to one of these 3 cannot be there. So whichever one is not there will complete an empty triangle. So let's say if this one's not there, then now you have got the empty triangle over there as well. So an empty triangle exists. Third case is when all the vertices have degree 2. Now, how do you have a graph where all vertices are degree 2? Think about that. Okay, so it means that, let's say I start here, right? This is connected to 2 things. I don't want to close a triangle, so it means that this must connect to another one. Now if I connect here, then the last vertex is stranded. So I can't do that, and if I can't do that, it means that they both connect to the last vertex, and it's actually just a pentagon. So it becomes A plus B, B plus C, C plus D, D plus E, E plus A are rational. I think this is cutting off the screen a bit, so let me just adjust that a second. There we go. You realize that we get the same contradiction as above. You once again get the sum is rational, and then if let's say you subtract off A plus B and C plus D from here, which are rational, you end up with E is rational, and then so is everything, which is a contradiction. Not a contradiction in the sense of, oh, so the question fails. This is a contradiction in the sense that you cannot have all vertices with degree 2, so case 3 doesn't happen, and if case 1 or 2 happens, an empty triangle exists. So therefore the answer is just n equals to 5. perhaps you're saying that, yeah, that makes sense. Like, this is actually meant to be that complicated, or like, it makes sense, right? This is from our IMO team training. Yeah, this sounds right, right? Yeah, the same question was in the APMOPS for last year. And for anyone that is not a Singaporean that is watching this, the APMOPS is a competition for primary 6, grade 6 students. It was one of, I really don't know if it was the last or the second last question. The APMOPS format is a 2-hour paper with a number of proving and a number of short answer questions. And somebody in Hwa Chong thought that it was a good idea to do this. I guess you're getting the point of this video by now, right? If let's say that you had a friend or you had a younger sibling that saw this question, the APMOPS last year, and then asked you for help, you would feel very stupid and say that I can't solve a primary 6 question. Maybe some of you that are watching this are in the senior team. You're in the national team. You can't solve a primary 6 Olympiad question. Or at least you can't find a proof, right? This is a proving question. Maybe you can guess it is fine. And then you find out that it is from actually our IMO team training. You see, one of the things that is very important whenever we do questions is to know where it comes from. We want to know where a question comes from so that 80-90% of the time it tells you the set of techniques that is relevant. For example, if you're doing the SMO Junior, you do not expect trigonometry to be necessary. If you're doing the SMO Senior, you do not expect calculus to be necessary. The problem is when we take that a bit too far beyond the 80-90% guideline of that it usually happens that way. And instead you treat it as, oh, because it comes from here, it must be simple. Or conversely, because it comes from here, it must be surely too hard for me to understand. Both directions are not very good. If you thought that it came from a very easy place and you can't solve it, you feel embarrassed and you keep on trying to use easy techniques to do it. On the other hand, if you thought it came from a difficult place, you would just skip the question entirely and not even try the question. And the truth is probably somewhere in between. And so back to the title. There's actually no title to this. There is no title for this video. The title for this video is actually just, sometimes it's better not to know too much. Do not matter solve too much. I always talk about knowing the context. Don't do that too much. Don't look at the SMO Junior question and assume that it must only be difference of squares. You should try it first. But if it doesn't work, it may be harder than you think. And also, conversely, do not look at SMO Senior round 2 question and assume it needs something super fancy. It may be easier than you think. That's what I have to say for now. Do give the IMO question a try, just as a standalone problem, or give the SMO Open question a try, if you prefer that phrasing. Thanks for watching. See you back again soon next time.